Remainders are flawed for the uniform gauge, yet they're on Euclid built our common stage. Our prime roots shape what we become, irreducible truths that time can't overcome. We embrace classes not congruent to our trace. We dwell with our inverse face to face. When power surge and all seems gone, faith ma points us back to one.
Previously, we discussed modular arithmetic and explained how to perform modular exponentiation. Such computations have wide applications in cryptography. However, when the exponent is large, the value of the exponential can become so enormous that even modern computers may struggle to compute it directly. Yet, there is one notable exception. When the base a equals 1, the result is always 1, regardless of the size of the exponent. To see how this can greatly simplify our computation, let us start with a concrete example. Assume we would like to compute 3 to the power of 2025 modulo 5. We begin with small powers. 3 to the power of 1 is 3 modulo 5. 3 squared is 9, which is 4 modulo 5. 3 cubed is 27, which is 2 modulo 5. 3 to the power of 4 is 81, which is 1 modulo 5. Wait! This is a great sign. Since 3 to the power of 4 is congruent to 1 mod 5, so is 3 to the power of 4k, for any integer k. Now by the division with remainder, 2025 equals 4 times 506 plus 1. It follows that 3 to the power of 2025 can be written as 3 to the power of 4, and then to the power of 506, before finally multiplying 3. By the rules of modular exponentiation, the first term is congruent to 1 to the power of 506, which is nothing but 1. Hence 3 to the power of 2025 is congruent to 3 modulo 5. We see how 3 to the power of 4 is congruent to 1 modulo 5 has greatly simplified our computation in this example. In general, suppose we are computing a to the power of k modulo n for some large k. If we happen to know that a to the power of b is congruent to 1 modulo n, then by using division with remainder, we can write k as b times q plus r for some integer q and some non-negative remainder r that is strictly less than b. Then, by the property of modular exponentiation, the original term a to the power of k becomes a to the power of b, then raised to the power of q, then times a to the power of r. The first part thus becomes 1, so the entire expression is equivalent to a to the power of r modulo n. In this way, we have switched from computing an exponential with an arbitrary large exponent to an exponent that is less than b, thus simplified the computation significantly. Now, the natural question is, does such b always exist? Furthermore, if it exists, then is there a systematic way to identify such a value b, instead of relying on the brute force or on some random luck? The first observation is that a necessary condition for such a positive number b to exist is the coprimality of a and n. Indeed, the required equation can be written as a multiplied by a to the power of b minus 1 is congruent to 1 modulo n. In other words, a to the power of b minus 1 acts as the modular inverse of a. The existence of such an inverse implies that a and n must be coprime. From now on, we always assume that the base a and the modulus n are coprime to each other, unless otherwise stated. In the next few sections, we begin with Fermat's little theorem, which applies when n is a prime number. After that, we will present Euler's theorem, which generalizes this result to any natural number n. These theorems will help us identify the number that are appropriate for reducing the exponents and simplifying the computation of modular exponentiation.
新了10岁